High-density lipoprotein, HDL, plays a critical and complex role in cardiovascular health. Often called good cholesterol, HDL is much more than a single number on a lab report. It's a key player in cholesterol transport, vascular protection, and even inflammation modulation. In this session, we'll delve into HDL's structure, function, its impact on cardiovascular risk, and the latest research on its role as a therapeutic target. First, let's start with a foundational overview. HDL is a unique lipoprotein within the blood, tasked with transporting cholesterol away from the arteries to the liver for processing and removal. This movement, known as reverse cholesterol transport, RCT, is at the heart of HDL's cardioprotective effects. For cardiologists, understanding HDL's various functions is essential since its benefits extend beyond lipid transport alone. In terms of composition, HDL has a high protein content compared to other lipoproteins, making it denser and smaller. Its structure includes apolipoproteins, primarily ApoAI and ApoA2, phospholipids, and cholesterol, both free and esterified. ApoAI, the main structural protein of HDL, plays a pivotal role in HDL function by initiating cholesterol efflux, particularly from macrophages and atherosclerotic plaques. HDL also all contains enzymes like paraoxonase, PO1, and lecithin cholesterol acyltransferase, LCAT, which confer antioxidant and anti-inflammatory properties to HDL particles. HDL synthesis begins in the liver and intestine, where immature HDL particles are produced. These particles are lipid poor and only become fully functional HDL as they gather cholesterol from cells through key transport proteins, ABCA1 and ABCG1. This maturation is essential, as fully developed HDL can facilitate the reverse cholesterol transport process, removing cholesterol from cells and atherosclerotic plaques and transporting it back to the liver. This pathway underscores HDL's crucial role in preventing and possibly reversing plaque buildup. Beyond cholesterol transport, HDL exerts anti-inflammatory effects by reducing the recruitment of inflammatory cells to vessel walls and inhibiting inflammatory cytokines like TNF and IL-6. Additionally, HDL supports endothelial function by enhancing nitric oxide production, which helps keep blood vessels flexible and reduces vascular resistance. HDL's antioxidant capabilities also protect against LDL oxidation, a key contributor to endothelial injury and plaque formation. While higher HDL levels have traditionally been associated with lower cardiovascular risk, simply measuring HDL cholesterol, HDL-C, doesn't tell the full story. Optimal HDL-C levels are generally above 60 mg/dL, while levels below 40 mg/dL for men and 50 mg for women are associated with increased cardiovascular disease (CVD) risk. However, recent studies highlight a complexity. HDL functionality, more than its quantity, may be the true predictor of cardiovascular outcomes. This functional aspect has given rise to what some term the HDL-C paradox, where higher HDL-C doesn't necessarily translate into cardioprotection, especially in patients with dysfunctional HDL due to factors like chronic inflammation. Adding to this complexity, HDL exists in subtypes, primarily HDL2 and HDL3, with different roles. HDL2 is larger, efficient at cholesterol transport, but more vulnerable to inflammatory alterations, whereas HDL3 is smaller with enhanced antioxidant functions. Understanding these subtypes is clinically significant, as patients with normal HDL-C levels may still be at risk if they have dysfunctional HDL or an unfavorable balance of HDL2 and HDL3 particles. In terms of clinical interventions, lifestyle changes such as regular exercise, smoking cessation, and a heart-healthy diet can modestly improve HDL levels and enhance its functionality. Pharmacologic approaches like niacin, which raises HDL-C, and CETP inhibitors, which increase HDL particle levels, have had mixed results in improving cardiovascular outcomes. For instance, CETP inhibitors such as anacetrapib raised HDL levels significantly, but didn't always lead to better clinical results. This gap in expected outcomes has further underscored the importance of HDL quality over quantity. Current research is focusing on HDL function. Cholesterol efflux capacity, EC, the ability of HDL to promote cholesterol removal from cells, is emerging as a strong predictor of CVD risk, potentially more accurate than HDL-C itself. Additional functional metrics like antioxidant and anti-inflammatory assays are also being investigated as clinical biomarkers. Research into genetic factors like mutations in the SCARB1 gene that impact HD function holds promise for new therapies aimed at enhancing HDL's protective properties. In summary, HDL is a vital, multifaceted component in cardiovascular health, far beyond its role as a simple cholesterol transporter. The latest understanding in cardiology emphasizes HDL function over its levels, focusing on cholesterol efflux capacity, anti-inflammatory properties, and particle subtypes as better indicators of cardiovascular health. Future therapeutic strategies may thus center on improving HDL functionality rather than merely raising HDL-C levels.